Welcome back. We completed the problem partially, which is problem number 5. Let's continue and then solve it. I think I gave it to you. Did you solve? Did you get the answer? I'm asking you the voltage. Ultimately, the voltage across the capacitor will go to 15 volt according to this timing diagram and the qualitative analysis. But asking for the voltage across the capacitor at a time t is equal to 1 millisecond. Okay. Now we need to continue from this time t1 to 1 millisecond. Now the voltage across the capacitor, right? It is charging exponentially. Then we have to take the equation. Voltage across the capacitor Vc is equal to V final plus V initial minus V final into e to the power minus t by tau. That is what we need to consider and we need to calculate. Okay. Let's see. Therefore, this is case 1, case 2. T less than 0 before closing the switch. T is equal to 0 plus exactly when the switch is closed. T greater than 0 after closing the switch. Now we got to know that your capacitor will be charging linearly till time t1, that is nothing but 0.5 millisecond, because once the voltage across the capacitor reaches to 5, this is 10 plus 5 15, your V0 cannot cross 15 because the maximum output voltage what you can get is nothing but 15 only. Once output voltage reaches to 15, then slowly, now virtual ground concept is not valid, right? Practically it is not valid. Then slowly it is not 10, it is like a comparator. Then slowly the current, whatever current you have, the current will be decreasing exponentially. Then this voltage will be lesser as the current is decreasing. While decreasing and then becoming 0, it will be charged to completely to 15 volts what you have. Whatever output voltage you are having 15, it will be going to that 15. But asking that the voltage across the capacitor at a time t is equal to 1 millisecond. Okay, let me erase this. Okay, therefore now let me take new time axis. This is what is my new time axis. Therefore here t dash is 0. Now what is the delta? We got to know t1 is 0.5 millisecond. Therefore what is this delta? This is 0.5 millisecond. Therefore t dash is equal to 0.5 millisecond, which is real time with respect to the switch time, that is 1 millisecond, right? Now why I am taking like that? Because I am taking this as initial voltage, then I am calculating. Therefore when I say initial voltage, initial time, that is what is the equation which we use, that is valid for it. Therefore now tell me, therefore we want to find case 4 t greater than or equal to t1, which is nothing but 0.5 millisecond. That is what we got. T greater than or equal to t1. Therefore now tell me what is that? We know that voltage across the capacitor is equal to V final plus V initial minus V final into e to the power of minus t by tau, right? Now we want to calculate, therefore t1 or 0.5 millisecond less than t less than 1 millisecond, whatever may be. Now this is what is my new time axis. For the new time axis, 0 is nothing but, therefore what is our initial time, new time axis, let me say t dash, that is what is my new time. Therefore now tell me what is your final voltage. Finally your capacitor is trying to charge to 15 only, okay, that is 15 volt. What is the initial voltage? Exactly with respect to new time axis, this is what, because we already calculated what is this, 5 volt at a time t is equal to 0.5 millisecond, t1 0.5 millisecond, initial voltage is 5. Then if you substitute what is voltage across the capacitor, Vc is equal to, with respect to new time, V final 15 plus V initial 5 plus V final 15 into e to the power of minus t dash divided by tau. Tau is nothing but r into c. R into c is nothing but, this is the time. Therefore this is r into c. Then what is this? This is nothing but 15 minus 10 into e to the power of minus t dash divided by r into c. Therefore now I want to know the change. This is what is the, if you define this is what your new time axis, then this is what is the value we are trying to calculate. Therefore whatever you are getting here, this is what your Vc, or I can say Vc dash. With respect to new time axis, that is what your incremental voltage. Therefore let me call this as Vc dash. Therefore this is what is your Vc dash, right? Then tell me at a time t is equal to 1 millisecond. This is nothing but the time, new time is nothing but, when I say actual time 1 millisecond means new time axis is nothing but 0.5 millisecond. Therefore this is nothing but 0.5 millisecond, right? At this time, what is VC dash? VC dash is nothing but 15 minus 10 into e to the power of minus 0.5 milli divided by what is RC value? R is nothing but 1K, C is 1 micro. 1K into 1 micro, 1 milli. Right? Milli will be cancelled. Minus 0.5, right? Minus 1 by 2. Then what is this? This is nothing but 15 minus 10 by root E. This is what is our VC dash. Therefore, what is root E? First of all, what is E? 2.7321. If you take like that, square root of it is 1.65. 10 by 1.65. You'll get 6.05. Then minus 15. You will get 8.939. Therefore, sorry, because initial voltage is already considered, this is not the step. Okay, this is what you can take. So for exactly time t dash is 0.5 millisecond, that is what is 1 millisecond. Therefore, that is what is our voltage across the capacitor. This is because initial voltage is already considered. The 5 volt is already considered. Okay. Therefore, now tell me, if you calculate what you get, this is nothing but at a time t is equal to 1 millisecond is nothing but time t dash is equal to 0.5 millisecond. Right? And what is this? If you calculate, I got 8.94, approximately 8.94 volt. 8.94 volt. This is what is voltage across the capacitor. This is VC at time switch time 1 millisecond. But ultimately your VC will be 15 volt at time t is equal to infinity under steady state. Therefore, under steady state, this is under steady state. Okay. But if you see your options, right? Options are 0 volt, 6.3 volt, 9.45 volt, 10 volt. Tell me what is the answer which is nearer to 8.94? That is 9.45 volt. You know, this is what is solved. This is what is. If you assume that op amp is ideal, you will get 8.94 volt. But people solved it instead of taking all these things which is complex. You just take that your capacitor will be charging exponentially, because when this is what, right, when it is exponentially, don't take any virtual current concept, just take it transient way, which is not correct. It will initially it will be faster, then only it will be going to exponential relation to satisfy KCL and KVL. Then if you do in that way, which is nothing but VC, if you solve in that way, you'll get the answer which is 9.45 volt. Okay, I'll tell that procedure also. But that is not accurate procedure. This is accurate procedure. The accurate answer is 8.94 volt, provided your op amp is ideal. Okay. Ideal means huge gate, input impedance is infinity, output impedance is 0, and bandwidth is high. Okay, take it. Case 4. Last session I explained till case 3, right? Now case 4. The incremental time, for the incremental time, because already we are starting initial voltage of 5, the incremental time which is 0.5 milliseconds, right? What is the voltage we got? That is nothing but 8.94 volt. If you follow my procedure, you will understand it. Okay. But I can give you approximate answer which is straightforward. Directly we can get it. Okay. That also I'll explain. Let's wait. Then that answer, whatever approximate answer with approximate procedure, right, that will match to 9.45. Okay. I'll explain. Done? Okay. Now another procedure, approximate procedure. But strictly speaking, this is accurate answer. Now tell me, for DC, is it DC 10 volts, 0 output, right? If it is DC, for DC capacitor acts as a open circuit. That's what that is true only under steady state. For a DC capacitor acts as a open circuit, that is true only under steady state. But before reaching to that open circuit state, there is a transient current which is what is flowing through it, right? That is the transient current which is what is flowing through it. Because of the transient current which is what is flowing through it, virtual ground concept has come into picture. That is what we used and then we solved the problem. But now if you ignore that, if you ignore the virtual ground concept and then treat like this is what is comparator and then charging, that is what is approximate answer, which is not correct answer. But if you do that, therefore tell me this is what is because if you think that for a DC capacitor is open circuit, even the switch is closed, let us say switch is closed, right? Your switch is closed here. Now only this is the capacitor. Now this is what is flowing like this. Therefore now let's see to the comparator, because for DC capacitor acts as an open circuit, but that is under steady state. That's why I told, right, under steady state the voltage across the capacitor will be equal to the 15 volt what we get. That is also satisfied with that procedure also. But this is 10. Initially if we say this is 0, 10 0 plus is more, you will get 15. If you treat it as a comparator, this is what is 15, which is constant. Your capacitor is trying to charge to 15 volt, right? This is the time t is equal to 0, right? Now tell me what is voltage across the capacitor. Your capacitor is trying to charge to 15 volt, then voltage across the capacitor is equal to V final plus V initial minus V final into e to the power of minus t by tau. What is V final? Final voltage is nothing but 15. And what is initial voltage? Initially capacitor is uncharged, right? Then if you substitute, what is VC? VC is equal to 15 plus 0 minus 15 into e to the power of minus t by tau, which is nothing but if you take 15 common, you will get 1 minus e to the power of, it is normal charging capacitor voltage. Voltage across the capacitor is VCC into 1 minus e to the power minus t by tau, provided it doesn't have any initial voltage. That is what is coming into picture. Now what is VC? Therefore we want to know VC, right? we need VC at time t is equal to 1 millisecond after closing the switch. Therefore what is VC? VC is equal to VC at, therefore 15 into, it is like VC of 1 millisecond. This is VC of t, right? This is voltage across the capacitor with respect to time t. Therefore VC of 1 millisecond is equal to 15 into 1 minus e to the power of minus t 1 milli. What is tau? Tau is nothing but 1 milli, right? Then what is this? This is 15 into 1 minus 1 by E, right? What is this value? 1 minus 1 by E, 1 by 2.7321, 1 by 0.366. Based on 1 minus 1 by 0.366 into 15. You are getting around 9.45. Therefore, you are getting around 9.45 volt. This is what it is. It is straightforward or not? If you treat this as, right? If you treat this as 15, then it is nothing but RC circuit. Your capacitor is charging through R and C. The time constant is nothing but R and C. Then we want to know initial voltage is 0, final voltage is 15. Then if you substitute, then at time t is equal to 1 millisecond, you will get 9.45. But remember, this is approximate answer. That is what is matching to the options what you have. Strictly speaking, right? The moment then, remember, simple. If it is open circuit, I agree, it is a comparator. That is under steady state. But during transient analysis, this is not open circuit. Your capacitor is acting as open circuit only for DC input, that too under steady state. But now tell me, if there is a transient current which is what is flowing, then only it will charge, right? 0 to 15 it will charge exponentially because there is a transient current. If there is a transient current, then definitely there is a feedback. If there is a feedback, op amp will come into picture. If op amp is coming into picture, then the virtual current concept will come into picture. Then it is trying to force. Op amp will give you the constant current to flow. Then you will see that voltage across the capacitor will increase linearly up to some point until V0 reaches to 15. Once V0 reaches to 15, then over virtual current concept is not valid because your output is saturated. Then remember, it is like exponentially increased. That is what we used, and then we solved. We got 8.94 volt. That is what is accurate answer, provided op amp is ideal or having huge gain and more bandwidth. This is what is approximate answer, but both are close to each other because linear charge, initially it will be linear, whether it is exponential or linear, it is almost linear. Therefore 8.94 versus 9.45, around I can say 10% of error, not even 10%, 5% of error. Okay, that is fine, that is acceptable. With this I can say chapter 4 is done. Level 1, level 2 problems are also over. Now we can go to chapter number 5. I'll give you 1 minute time, try to write it. This is what is method 2, approximate method. This is what is approximate method. Approximate method. Over? Done. Now we can go to chapter 5. Okay, what I do, maybe instead of continuing this session, it's better to stop this session and then continue a fresh session, because the video will come under workbook problems, right? Student workbook problems. But this is concept. Chapter 5 is concept. Therefore, we will see chapter 5 in the next session. Meet you in the next session. Thank you.